In this lecture, we continue with the idea of limit, except now we're going to do the formal definition of limit. Rather than finding limits, we're going to discuss how to prove that a claimed limit actually is the limit. What do we mean by something being the limit of a function at a point? Okay, so we're going to start with a little game, and then that will motivate the formal definition of the limit of a function. Okay? So let's say that you say to me, the limit as x goes to 1 of 2x is equal to 2. I say, well, what do you mean by that? And you say, well, as the values of x get really, really close to 1, the value of 2x gets really, really close to 2. I'm not sure what really, really close means. And so I don't like your claim here. That's wishy-washy language. And I'll say, well, all right, what do you mean by really close to? Well, you can say, well, if you get really, really close to, okay, same things over again. All right, let's be specific. I will set you a challenge. Okay, show me that there's an interval with 1 in the middle. So an interval that looks like 1 minus some number up to 1 plus some number. We're going to take 1 out of it because you said x gets really close to 1, but it's never actually equal to 1. Okay. And you show me that if you take the numbers in that set, that punctured interval, then you get numbers. All the numbers that you get, when you feed those numbers into the function, and then you consider the numbers that the function spits out. The function spits out numbers that are all within, let's say, 0.1 of 2, and then maybe I'll believe you. Okay. So you say, all right, you set the tolerance that the function value 2x, the difference between the function value 2x and the claim limit 2, that should be less than 0.1. And since I can have maybe numbers bigger than 2 in one, depending upon which direction I'm coming from, I might end up with numbers that are bigger than 2 or less than 2. So I'm going to use an absolute value so I don't have to worry about that. Okay. So I've got absolute value of 2x minus 2 must be less than 0.1. Okay. Well, I can have that if, let me factor out the 2 and then divide by 2. So what I see is that if I have absolute value of x minus 1 is less than 0.05, then the absolute value of 2x minus 2 is less than 0.1. If x is within 0.05 of 1, that is, if x is in the interval from x minus 0.05 up to x plus 0.05, then I get that the absolute value of 2x, the function value, minus 2 is less than 0.1, and 0.1 was the tolerance you set me. So I have answered your challenge, and what I have is that the absolute value of x minus 1 less than delta, if I set delta equal to 0.5, implies that the absolute value of 2x minus 2 is less than 0.1. If I am within 0.05, if all the x values I'm considering are within 0.05 of 1, then all of the function values, when I feed those numbers into the function, all the values of the function which it spits back are within 0.1 of 2. I said, wow, all right. I still don't believe it. Let's set a really tough tolerance. Let's make it 0.01. So you say, all right, I will give you an interval. I will show you an interval around 1, which if it's small enough, I can guarantee that when you feed those numbers of that interval into the function, then the function will spit out values that are within all the values that the function spits out are within 0.01 of the claim limit 2. Okay, so then you say, all right, you wanted absolute value of 2x minus 2 to be less than 0.01. That's equivalent to twice the absolute value of x minus 1 being less than 0.01. And then that happens whenever absolute value of x minus 1 is less than 0.005. If I divide everything through, if I divide the inequality through by 2, that's what I get. So what that means is that if x is within delta equals 0.05 of 1, then the absolute value of the function 2x minus the claimed limit 2 is less than 0.01. So if I get that close to 1, if I get within 0.05 or less to 1, then if I have such an x, then f of x is within 0.01 of 2. And I'll say, well, okay, look, this could get tedious. Let's just say that I can pick any number bigger than 0. Epsilon is traditionally the number we talk about. So I can take any epsilon greater than 0, and then I'll be able to make that as small as I like. So I can make it 10 to the minus 7, 10 to the minus 100, or whatever. I can make it as small as I like, and you show me that you can, that there's some interval on which if you feed the value, if you feed the x values from that interval into f, then the values f of x that it spits back are all within epsilon of your claimed limit 2. And you said, look, all right, it's the same thing. Absolute value of 2x minus 2 is less than epsilon, or if and only if twice absolute value of x minus 1 is less than epsilon. Let me divide through by 2, and I get that absolute value of x minus 1 is less than epsilon over 2. Okay. All these steps are reversible, so that means that if I take x values that are within delta equals epsilon over 2 of 1, then I get function values that are within the required tolerance epsilon of 2. Okay, so basically this is what's going on every time we do formal epsilon delta proof, which I'll show you now what's the definition. Okay, so we were saying this phrase x within delta of x naught, right? Before our x naught was 2. So that means absolute value of x minus x naught is less than delta. We also have a requirement that x is never equal to x naught. Okay, you'll see later when we do derivatives why that's necessary. So we don't want x equal to x naught. So then if 0 is less than absolute x minus x naught, then we're guaranteed that x will never be equal to x naught. So now what we want is that 0 less than absolute value of x minus x naught less than delta implies that the absolute value of f of x minus the claimed limit should be less than epsilon. Okay? So f of x, the value spit out by the function f of x, to be within epsilon of L, we translate that as absolute value of f of x minus L is less than epsilon. Okay, so now we can give the formal definition of the limit. We say the limit as x goes to x naught of f of x is equal to L if for every epsilon greater than 0. So in principle, you can make epsilon as small as you like. If for every epsilon greater than 0, there exists some delta, which will in general be a function of epsilon. There exists some delta dependent upon epsilon greater than 0, such that 0 less than absolute x minus x naught less than delta implies that the absolute value of f of x minus L is less than epsilon. Okay, so you can look at it this way. If we're taking the limit as x goes to c, and we're considering an interval of radius delta, so it ranges from c minus delta to c plus delta on the x-axis there. And then you feed those values into the function f. And you're claiming that the limit of that function at c is L. Then all those values from that interval, from c minus delta to c plus delta, excluding c, should lie within L minus epsilon to L plus epsilon. And if this works for every epsilon, that means that the function values can be made arbitrarily close to L. This is what we understand by the limit. Okay, so think of it as a game. Your opponent picks epsilon, you have to find a delta, so that x within delta of x naught, but not equal to x naught, implies that f of x is within epsilon over L. Okay, and now we will go on and we will consider some examples.